Hello and welcome to Easy Projects. So don't you hate when you look through your junk pile to find a transistor to use for a project and you find something like this 2N1613, but you'll have to find the datasheet to know the pinouts, right? Well, today I'll try to solve that problem by building a transistor tester. So I just want to build something very cheap and very simple, like a device with some contacts in it, and when you put the transistor in the correct way round, an LED will light up. So that could be something with like 5 contacts in a row and a pin combination like this. This will allow every possible pin out of a transistor, so you can go collector emitter base collector emitter, and you can flip it around and go back. And that way you covered all possible combination of the pins. And of course the LED should only light up when you hit the correct pin out. As I said, I want this to be cheap, so we can only use cheap components. And I wanted to give the pinout of both NPN and PNP transistors. I would like it to be able to measure the gain, not necessarily display it on the device itself, but it could be something like you could plug in the multimeter and get a gain reading. And I want it to be battery powered. And as I already mentioned, the first thing that came to my mind was this row of 5 contacts where you just move the transistor across and try until you get the right pin out. And the way to test the transistor could be something like this. If you have, say, 1 milliamp flowing into the base of a regular NPN transistor, you would be able to measure the current going into the collector. And you could both tell if you've put the transistor in the correct way and what the gain is by measuring the current going into here. But of course there's a problem that if you put it in the wrong way and you connect the collector to the base and you connect the base to the collector, you would get all of the current flowing into the base, and that would destroy the transistor. So we need to be able to limit the current on the collector as well. So we'll put a resistor here. And that is actually not a bad thing, because now we can also measure the current by measuring the voltage drop across that resistor. So for an NPN transistor this could actually be working quite well, I think. And by connecting 2 comparators to this resistor, we would be able to make our LED that would turn on when a good transistor is put into the circuit. And also if we put in the transistor the wrong way around, we could end up connecting the base to the collector terminal and the collector to the base terminal, and the emitter is still connected to the emitter terminal. But this would allow all the current that can be drawn through this resistor to be drawn to ground, plus the current from the current source up here. But this resistor will ensure that the transistor will not be damaged. And we can set the limit of the comparator to take this into account, so it will not turn on the LED if we put it in the wrong way around. And also another example where the base is connected to ground and the collector is connected the right way around and the emitter is connected to the current source. This will of course mean that no current is being drawn through this resistor, and there will be a 0 voltage drop. And we can also program the comparator so it will take into account that this is not a good configuration. So this was for our NPN transistor. And as it so happens for the PNP transistor, all we need is to flip this current source around so it will try to pull current out of the base. And we will need to relabel these 2 terminals. So if this was the emitter and this was the collector, this will now be the emitter and this will now be the collector for the PNP. The only problem with this is that we will get an error of 1 in gain, because the current going into the transistor will all come through this resistor here. So we will get both the base current and the current through the transistor. And to be correct, we would only want to read the current through the transistor and compare that to the known base current. But I could live with an error of 1, that's not a problem at all. And if we just stick with our NPN transistor for a while, we will need to come up with a circuit that can light up the LED when we have connected the transistor in the correct way around. And of course, if it's connected the wrong way around, the LED should not light up. And I call these two nodes for T plus and T minus. So if we look at this circuit, T plus is connected to these two nodes and T minus is connected to the middle here. Of course, T plus will never change, that will always be 5 volts, but T minus will change once you connect a transistor to the device. Both the T plus inputs are divided down to give another voltage, and that is fed to the inverting input of two comparators. The output of these comparators are connected through a resistor and an LED, and the non-inverting input is connected directly to T minus. And if we say there's nothing connected to the device, there will of course be no voltage drop across our test resistor, and this voltage will be 5 volts as well. And if this voltage is 5 volts and these are both lower, both these comparators will be on. And since they're both on, the LED will be off because no current can flow. But once we connect a transistor to the device, this voltage will drop. And if we have connected something in the right way around, it might drop to, let's say, 4.2 volts. So that will be lower than this, but higher than this value. So this comparator will turn off and this will stay on. And now current can flow through the LED and back into this comparator, so the LED will light up. If we connect a device in a wrong way around, so this will be shorted, there will be almost 0 volts here, and that will be lower than this voltage, so this will also turn off, and of course this is still off, and the LED will turn back off. And we can also connect something in a wrong way around that will not short out, and this will keep staying at 5 volts and it will still be off. So in theory this circuit should work. It's just this voltage is too low. I already know that because there's a 0.6 or 0.7 volt drop across the transistor. And this voltage needs to be above that. I just chose some random resistors here as a proof of concept. So let's try to find the breadboard and test all this stuff. So here is the first part of the circuit, and this is the part that we will actually plug the transistor into. I chose to use an LM334 current source, and I have set a base current of 10 microamps instead of the 1 milliamp that I was talking about before. And that is of course because if we have 1 milliamp we will have maybe 200 or 300 milliamps of collector current, and not all transistors can handle that, so it's better to lower that a bit. And all we need to set the current on this thing is one resistor, and in this case it's 6.8 kilo ohms. So this is what will drive the base, and I have all this connected to a 5 volts at the moment. And up here for the collector I have a 100 ohm resistor. And with a 100 ohm resistor and 10 microamps on the base, we should be able to measure the gain in millivolts across this resistor. And the collector over here I have going off to ground. So let's test this and see if we get 10 microamps of base current. And I will just measure from the ground to the base terminal, and we got that down here as well. And that's 9.8 microamps, and that's good enough. The LM334 has a 3% internal accuracy, so that is within spec, and the resistor is at 1%, so we also need to take that into account. So now let's try to measure the gain of a random transistor. And this is an NPN, of course, we're only working with NPN right now. So let's put this one in. So now I have connected the ammeter in series with the collector, and let's try to measure the current. And we get 3.29 milliamps, and that is of course 3300 microamps. And if we divide that by 10, we will get a gain of 330. And as predicted, that should be the same value in millivolts across this resistor. And I mean, it's close enough. So let's try to see what will happen if we connect it the wrong way around. And if we swap the base and the collector, you can see it will pull as much current as it possibly can. That gives us 36 milliamps. And this voltage we will need for setting up our comparator. So if we connect it completely back to front, with the emitter to the collector here, the collector to the emitter, and the base is still at the base actually, but that will give us a 3.3 milliwatt drop, or 33 microamps through this resistor. And that is actually a gain of 3 compared to the current going into the base. So we will need to set a minimum value as well. That should be a little higher than this. And let's get back to our comparator circuit again. So I have just put in some values here. For the upper voltage I have chosen 4.98 volts, and that should equal a gain of 20. Now I'm not sure of this value, maybe we'll need to correct it later. And to get this we'll need a resistor of 250 kilo ohms, but I don't have that, so I'll put a 270 in. And to set the lower limit, we can use our test resistor as an example. When we connected the base to T- here, it should short out the test resistor. And we saw that the voltage drop across the transistor was 1.2 volts, because it dropped 3.8 over the test resistor, leaving 1.2. So we'll need to choose a value above that, so I just set it to 1.75 volts. And again, we might need to change this. And then this resistor should be 10.4K, but we'll put a 10K there. I'm planning to have a 9 volt supply on the comparators, and they cannot go to 9 volts or to ground. They will be about 1.3 volts in each end. So the maximum we should be able to see across this diode should be 7 volts. So we can choose this resistor to give us about 10 milliamps at 7 volts. And we need to subtract the drop of the diode as well, so about 5.8 volts. So that should be 580 ohms. So we'll put a 680 ohm here just to be on the safe side. So let's try to build this up on the breadboard and see if it works. So I have added the comparator circuit over here, and that is exactly as drawn on the schematic. I used a TL074 opamp as a comparator, and I'm feeding it with 9 volts. I have added a 5 volt regulator, and I'm powering the rest of the circuit with that. So let's try to switch on the power supply. And our LED comes on, and that's a good thing because the transistor is still in there. So let's try to remove it, and let's hope the LED will turn off. And it did. So now if I put it in backwards, nothing should happen. And that's not on. So I'll try to connect the base to the test resistor and still connect the emitter to ground, so that should allow the transistor to short out this resistor. And the LED was not supposed to turn on here, so there must be something wrong with our low voltage. So let's measure our voltages. I will hook this up to my ground over here. And this over here should be our high voltage. Oops, I think I found the problem here. The LED was supposed to be connected across the outputs of the comparator, but I didn't. I connected it over here. So let's try to move this over here and see if that solves the problem. And the LED turned off, so that could be it. But let's just measure the voltages anyway. And let's measure the low voltage, and that should be 1.75 volts, but we didn't get the exact resistor, so there could be a bit of an error. And that is 1.8 volts. And let's see what we are getting in on the T minus. And we're getting 1 volt, and we still have the transistor to short out this resistor, of course. So let's take our high voltage. That should be this guy. We have 4.824. And that's actually a bit low, but that could be the voltage of the regulator. That's a bit out. No, that's okay. So I don't know what went wrong there. I need to check if I put the correct resistor in there. Yeah, well, that seems to be correct, so it must be something to do with these crappy wires. And there is indeed something horrible wrong here with these wires, because we have 5 volts at the regulator. That goes through one wire here into the breadboard and out for another wire to this resistor over here. And if we measure that resistor, we already got a drop there, and it was actually much worse just a moment ago. There, you can see he has something dicky with these contacts, so, and we're only pulling like 30 milliamps or something through this, so let's try to measure that again. Yeah, and after playing around with just the wires, we are actually getting 4.926 volts. So let's try to remove the transistor. And of course the LED should still be off. And it is. And let's try to put it in the correct way around again. And the LED lights up. So that seems to be just fine. So let's see if the LED will turn on at a gain of 20 as it was designed for. And we can do that by removing the transistor and putting a resistor in instead. And we can choose the value to simulate a gain of 20. And that should be 0.2 milliamps through this resistor. And since we're using 5 volts, that should be 25 kiloohms. So I have a 22 kilo ohm here, and if we put that in, the LED should light up. And it doesn't. So we need to trim the values a little low here. So I have to go down to 15 kilo ohms before it turns on. But again, our value here was also a little bit out, so that could be the reason, or that is the reason. So I tried to fix all this contact resistance, and now I can get it to light up with 18 kilo ohms, and that should be around a gain of 27. That's still a bit on the high side, but it should do for this test. And with the lower value of 1.8 volts, that should give a maximum gain of 3200 before the LED goes out. And that should be about right if the transistor is connected the wrong way around, so it will short out this. The LED will not turn on. If nothing is connected, the LED will not turn on, but if it is connected the right way around, we can have a gain between 27 and 3200. And I will adjust the lower part to about 20, or maybe 15. So now I am happy with this circuit. It just needs to be trimmed a little bit, but we have to come up with something for this to be able to test PNP transistors as well. And I think we can just flip this current source around so it will try to draw current out of the base instead of trying to push current into the base. And we can do that with a double pole switch that has 2 on positions. So I'll try to draw that up. So I have drawn up the switch here, and it is of course a double pole switch, so all this will be isolated from all this. For an NPN transistor we want this node, the V plus of the LM334, to be connected to 5 volts. And we want the V minus of the LM334 to be connected to the base. And the base is connected to ground via the emitter of the transistor, of course. But for a PNP, we want to pull current out of the transistor, so we want the V plus to be connected to the base. And we want the V minus to be connected to ground. And the switch will of course switch both poles at the same time, so it will either be connected like this, or it will be connected like this. So we can connect the base across the switch, because this cannot be connected while this is connected. It will always be disconnected, or the other way around. And with the switch connected, it should hopefully still work with an NPN transistor. And it does. And I have a PNP transistor here, so let's try to connect that one. And of course we shouldn't expect it to work before we switch it to PNP. And now it is working. So if we disconnect this, the LED turns off. If we put it in the wrong way round, the LED is still off. And if we try with the NPN, it doesn't turn on either. So now this seems to be working just fine, and I will try to do a few adjustments to this comparator circuit over here to get the LED to turn on at the correct gain. And I did also find out that some transistors have a breakdown voltage, a reverse breakdown voltage of about 5 volts, so that is actually the supply I got here. So I think I should lower that to 3.3 volts instead, just to be sure that it doesn't blow any transistors. But I am going to correct these values anyway, so I'll just have to take that into account. And then put a 3.3 volt regulator in instead. So I have just put a 3.3 volt regulator in here instead. I did nothing to the rest of the circuit, just to confirm that it is working, and I calculated that with a 1 volt drop across the transistor we are trying to test, we can still get 2300 in gain, and that should be just fine. So now I'll just have to trim these values for the 3.3 volts. And I'll set the lower voltage to 1 volt instead, because I think that's more than good enough. There shouldn't really be any transistors with a drop of more than 1 volt, I think. So I think I have got the resistors all sorted out for this comparator circuit. These top ones here I could just use the same. That will give us a voltage of 3.288 volts. We can of course always change it later if it needs that. But this lower one I had to change to get about 1 volt at the top part of the gain. So I changed this resistor to 4.7k. And of course these voltages are now 3.3 volts, and T minus can only go to 3.3 as well. And it will still be able to go down to about 0.6, 0.7 volts, depending on the transistor you connect. So as I said, I'm using the TL074 opamp as a comparator. And this is indeed not a very good comparator, but it is cheap. As I said, I wanted it to be cheap. So the problem is with this lower voltage, and also if we had a high voltage up at the 9 volt mark. But we have this down here near the ground rail. And the problem is that it may not be able to tell the difference between say 1 volt and 1.3 volts or something. I think it should be doing okay for about 1.3 or 1.4 volts, but I'm not sure about that. But that could mean that if, even though we have 1 volt here, and if we have perhaps 1.3 volts here, it could still think that this is higher and then set the output low. Or it could actually be the other way around, so if this one gets to, say, 0.8 volts and this one is at 1 volt, it could still think that this one is higher and keep the output high. So I have no idea if it's one or the other, but we can try to do a test to see where these minimum voltages are. So I have just set up a small comparator circuit here with some voltage dividers that I can adjust. And I have connected a multimeter to the inverting input, the non-inverting input, and to the output. And right now the inverting input is lower than the non-inverting, so the output should be high, and it is. I am powering this from 9 volts as well, and as you can see the output cannot go to 9 volts either, and it cannot go to 0 volts. But that will be just fine for our circuit. We don't need it to go to either 9 or 0. But let me try to adjust this inverting input so it gets higher than the non-inverting. And as you can see, the output has now gone low, or as low as it will get, 1.4 volts, but that's just fine. Let me just try to adjust this a bit. And as you can see, it does change within a few millivolts, so that is just fine. We don't need high precision or anything, but so if it could do this down at the low voltages, that would be just fine. So let's try to test that. So I'll try to set the non-inverting input to 1.05 volts. That would be the same as the transistor tester circuit. And let's drop the non-inverting. And the output should stay high until we get just below this voltage over here. Oops, and as you can see it have changed already, but we're still way higher than this voltage, so that's a problem. And the gain is very bad also. Normally it just changes within 1 millivolt or something. Here it's hundreds of millivolts. But actually, as long as it is this way around, that it goes low before this reaches 1.05, that's actually okay. Because that would just turn off the LED at a lower gain, and we would have to rise this voltage anyway. So let's try to drop it down. Oops! Now see, that's not good, because now the non-inverting is lower than the inverting input, but the output is high. So that would mean our LED would turn on. But at least now we know that there's a problem here, so let's try to raise these voltages until we can get this to behave normally. So let's try to set this to 1.4 volts. And now the output is high-ish, so that should be correct according to this. So let's increase the other voltage. We don't want this to change before this hits 1.4 volts. And it already did, so let's give this another turn. So this is actually very, very bad, because we have to go to about 2 volts before we can get it to even change within 100 millivolts. And as you saw, at about 2.5 volts it changes within 1 millivolt. So, but then again, we don't need very much precision. We just need to be sure that the LED would not be on if the transistor is connected the wrong way around, so it's shorting the test resistor to ground. There will be a voltage drop of about 0.6 volts. So as long as this goes low before this hits this one, we should be fine, as long as it's not the other way around. But we have to come up with a solution so that when this gets below 1 volt, this will go high again. So let me just try this again. And yet it actually still does with almost 2 volts here, and this at 0.8. So we'll have to fix this because the transistor will have a drop of about 0.6 volts. So that would actually mean that it could turn on the output again. And I think I have solved the problem now, so let's try to turn this voltage down again. And now 7.8 volts is a high at the moment. And yeah, that went low, so we're still a couple of 100 millivolts out, but again, we can live with that. That's not precision that we're after. Just want to make sure that it will not go high again. And we're down to a couple of hundred of millivolts on this, and this should not get lower than 0.6 anyway, so we are way lower than we need to be. And this is still low. But if we turn it down just a bit, it actually does get high again, but only when we reach about 150 millivolts here. So what did I do? I simply added a diode on the ground path, so everything has to go through a diode to get to ground except for the comparator. So that would in fact mean that we are lowering the negative supply for the comparator by 0.6 or 0.7 volts. And as it turns out, that is actually all we need, so it is not a very good way of doing it, but I think it will work, so we'll try to do that. And the reason that it is not a good idea to do this is because the voltage drop across the diode actually changes quite a bit with the current going through it, but we only need to draw about, I don't know, a maximum of 33 milliamps anyway, so that should be fine.